Hello students, we are considering about the topic elements of group 16th, 17th and 18th. Today we shall about the allotropy, what is the meaning of allotropy and which are the different allotropes of group 16 elements. Group 16 elements are obtained in different allotropic forms. You know that allotropy is a property of element in which these elements are obtained in different, or they have different physical properties but having same chemical properties. Their physical properties, that means they can have different color, they can have different melting point, they can have different density. These physical properties are different, their structural arrangement can be different, but they show the same chemical properties. For example, we have studied about the allotropes of carbon, that is diamond, graphite, fullerene. These are the allotropes of carbon. In 11th standard we have studied about the allotropes of phosphorus also. Now here we shall consider about the allotropes of group 16 elements. These elements you know are oxygen, sulfur, selenium, polonium, tellurium and polonium. Now all these elements have different allotropes. Now oxygen can be obtained in two forms. Two allotropes of oxygen are O2 and O3. Sulfur is obtained in different, or many allotropes of sulfur are there, but the most common or important allotropes of sulfur are rhombic sulfur, or it is also called as alpha sulfur, and the second one is monoclinic sulfur. It is called as beta sulfur. Different allotropes of sulfur are there having the chain of sulfur atoms. You know that sulfur shows the property of catenation, that is sulfur atoms are covalently bonded with each other. Near about 6 to 60 sulfur atoms can be arranged in different forms. Here the main allotropes of sulfur are rhombic sulfur and monoclinic sulfur, which are also called as alpha sulfur and beta sulfur. The selenium has two isotopes, that is red selenium and gray selenium. Tellurium has again two isotopes, crystalline and amorphous. Crystalline and amorphous. Remember here, these sulfur has the allotropes which are in crystalline form, and polonium has the allotropes as alpha polonium and beta polonium. All these are the allotropes of the elements which are present in group number 16. Now we shall consider about the allotropes of sulfur which are important, that is rhombic sulfur and monoclinic sulfur in detail. We shall consider about which are the properties of these, or how these two allotropes differ from each other as considered with the physical properties, and so which are the distinguishing points between rhombic sulfur and monoclinic sulfur we shall consider here. Now we have to consider about rhombic sulfur, or it is called as alpha sulfur, and monoclinic sulfur, or it is called as beta sulfur. How the properties of physical properties of these two allotropes of sulfur differ from each other we shall consider now. The first property is color. Rhombic sulfur is pale yellow in color. It is pale yellow in color. Monoclinic sulfur is bright yellow colored solid. Bright yellow colored, both are yellow colored, and this is bright yellow colored solid. The second property is, now if you consider the melting point of rhombic sulfur is 385.8 Kelvin. Rhombic sulfur has the melting point 385.8 Kelvin, and here monoclinic sulfur has the melting point which is greater than this rhombic sulfur. This value is greater than this. Remember, here melting point is 385.8 and it is less than the melting point of monoclinic sulfur. Now if you consider the crystal, what is the type of crystal? This is orthorhombic crystal. We have studied about orthorhombic crystal in 11th or solid state. In topic solid state, we have considered about the different structures. Here orthorhombic structure is there, and monoclinic sulfur has needle shaped. This is needle shaped structure. You can show this structure like this. You know, needle. These crystals are like this. So here this structure of monoclinic sulfur is needle shaped, and this is orthorhombic, that is, you can show this like this. So like this structure of rhombic sulfur you can obtain, that is, it is orthorhombic structure, and monoclinic sulfur has needle shaped structure. Now if you consider about the density, if density is considered, now density of rhombic sulfur is 2.06 gram per cm cube, 2.06 gram per cm cube, and that of monoclinic sulfur is 1.98 gram per cm cube. So remember, here density of rhombic sulfur is greater than the density of monoclinic sulfur. Here it is 2.06, the unit of density is gram per cm cube, and here it is 1.98 gram per cm cube. If you consider the next property, that is solubility. Here remember, rhombic sulfur is insoluble in water. It is insoluble in water, and it is soluble in carbon disulfide, that is CS2. It is soluble in CS2, that is carbon disulfide. Here monoclinic sulfur is also soluble in carbon disulfide. It is soluble in CS2. So solubility of rhombic sulfur and monoclinic sulfur is, here rhombic sulfur is insoluble in water, but it is soluble in CS2, which is called as carbon disulfide. The next property is structure. Here remember that due to the catenation property of this sulfur, here S8 molecule is obtained. 8 sulfur atoms, they form the covalent bond with each other, and so we can have S8 molecule, and this S8 molecule is having puckered ring structure, or it is also called as crown shaped structure. Both these are having S8 molecule, that is sulfur is obtained in the form of S8 molecule. 8 sulfur atoms, they are covalently bonded with each other. You know, this is called as the property of catenation, and this structure is like a crown or puckered ring structure, and this structure can be shown like this. Suppose we have this structure here. You can show this like this. This is like the ring, or you can say it is like a crown, and so this is called as puckered ring structure or crown shaped structure. Both these allotropes of sulfur have the same structure, that is puckered ring structure or crown shaped structure. Now, how these are prepared? What is the method of preparation of these two allotropes of sulfur? Remember here, this sulfur, rhombic sulfur, is soluble in CS2, and so it is dissolved in CS2, and this solution is evaporated, and after the evaporation you can obtain the orthorhombic structure, that is rhombic sulfur is obtained. Monoclinic sulfur is obtained by melting the rhombic sulfur. Monoclinic sulfur is obtained by melting the monoclinic sulfur by heating it, and you can melt it in a dish and it is cooled. After melting, it is cooled and hard crust will be obtained. This crust, here holes can be created in that dish. The crust is obtained, then two holes are created, and this remaining solvent or liquid is drained out, and you can obtain needle stepped monoclinic sulfur like this. Here remember, rhombic sulfur is obtained by dissolving the bars or sticks of sulfur in CS2, that is carbon disulfide, and then it is evaporated and you can obtain the crystals of rhombic sulfur or alpha sulfur. And monoclinic sulfur is obtained by melting rhombic sulfur. It is cooled in a dish, the crust is obtained, hard structure is obtained, some holes are created in that crust, and the remaining liquid is drained out, and then you can obtain the needle shaped structure. Like this, we have the two main or important allotropes of sulfur, that is rhombic sulfur and monoclinic sulfur. You have to remember the physical properties of these allotropes of sulfur. Now remember here, the sulfur which is present in S2 form. You know, sulfur can be obtained from 6 to 20 sulfur atoms can be combined together, and you can obtain different allotropes or different rings. The S2 here, this S2 molecule or S2 allotrope of sulfur, it is the dominant species, and this sulfur allotrope is paramagnetic in nature. Remember here, this is paramagnetic in nature because it can have the unpaired electrons. The question can be asked, which allotrope of sulfur is paramagnetic in nature? Due to the unpaired electrons present in anti-bonding molecular orbitals, S2, this allotrope of sulfur, is paramagnetic in nature. Now remember again one property here, stability. If you consider of these two rhombic sulfur and monoclinic sulfur, the temperature here, it is important, below 369 Kelvin. Below 369 Kelvin you can obtain rhombic sulfur, and if you increase the temperature above 369 Kelvin, here this rhombic sulfur can be converted into monoclinic sulfur. That is, at 369 Kelvin both these rhombic and monoclinic sulfur can be obtained, and that temperature is called as transition temperature. Remember here one property, I have forgotten this property, stability. Here below 369 Kelvin, that is near about 95 degrees Celsius temperature, here rhombic sulfur is present, and rhombic sulfur can be obtained below this temperature. If you increase the temperature above 369 Kelvin, you can obtain monoclinic sulfur, and so at 369 Kelvin both these allotropes of sulfur can be present, and that temperature is called as transition temperature. So remember all these properties here. Now we shall consider about the oxoacids and oxoacids of sulfur. What are oxoacids? If you consider simply acid, if we have only acid, you know that acid is a substance which donates proton, that is, which donates H plus ion, or you can say that the substance which contains hydrogen, that is, hydrogen compound is an acid according to Arrhenius theory, also according to Lorry-Bronsted theory also. So remember here, oxoacid is an acid which contains oxygen also. That means here we have oxygen in that acid. That acid is called as oxoacid. Generally, the non-metal, and when it has OH group, then it is called as oxoacid. Remember, oxoacid is an acid which contains oxygen. So there are different oxoacids of sulfur. We have to consider about different oxoacids and which are their structures. Now different oxoacids are there, but most of them, some of them cannot be stable, they are unstable, they cannot be isolated, and some of them are stable. We shall consider these stable oxoacids of sulfur. Here remember, you know these two acids, sulfurous acid having the molecular formula H2SO3 and sulfuric acid, that is H2SO4, that is here the prefix suffix is OUS, and here this is IC. OUS, this suffix is for less oxidation state. If the oxidation state of sulfur is less, then that is called as sulfurous acid. You can calculate the oxidation state of sulfur here. Remember here oxidation state of hydrogen is +1, so here +2. Oxidation number of oxygen is -2, that is here it is equal to -6, and so for the summation of these oxidation number of all these, that is hydrogen, sulfur and oxygen, must be 0, and so here sulfur as the oxidation state +4. If you consider the oxidation state of sulfur in sulfuric acid, here +2 of hydrogen, -8 of oxygen, and so sulfur as the oxidation state +6. That means here the oxidation state of sulfur in sulfurous acid is +4, in sulfuric acid is +6. So remember here, on the basis of oxidation state, the suffix, that is OUS, and IC, that is ic and us, sulfurous having less oxidation state, sulfuric having high oxidation state. Here remember, in any oxoacid the most common thing is we have S double bond O and SOH bond. Here S double bond O and SOH bond is compulsory in all these oxoacids. Now we shall consider how these structures are prepared. Now remember here, in sulfurous acid having the molecular formula H2SO3, the compulsion is of S double bond O and SOH. So here one OH bond is attached to sulfur, double bond between sulfur and oxygen. That means here we have H, S and O2. What is remaining here? One oxygen is remaining and one hydrogen is remaining, so one OH group is attached here. And here see the number of electrons in the outermost shell of sulfur are 6, and so one lone pair is shown here. So you have to remember how to draw the molecular structure of oxoacids of sulfur. The main thing you have to remember is sulfurous acid and sulfuric acid. Both are the basic oxoacids of sulfur. Sulfurous acid have the molecular formula H2SO3. In any oxoacid, you have to remember these two bonds are compulsory, that is S double bond O and SOH. And so when you have to draw this structure, first draw S double bond O and SOH. The remaining is one OH bond, and so show this OH bond here, and this is the structure of sulfurous acid. Now sulfuric acid, it is having the molecular formula H2SO4. Again S double bond O is there, SOH bond is there compulsory, and what is remaining here, H and two oxygen atoms are remaining, so double bond O and single bond OH. This is the molecular formula H2SO4. Remember, in H2SO4 there are two double bonds between sulfur and oxygen, and two OH bonds, OH and S bonds are there. The third oxoacid of sulfur is di or Pyrosulfuric acid, having the formula H2S2O7. Here you know that di means 2. Remember, the next all acids are formed due to the sulfuric acid. Here sulfuric acid is basic in all these oxoacids. Di means 2 and pyro means when you heat these two sulfuric acid molecules, here one H2O molecule is lost, one H2O molecule is less, and so remember here when you take two H2SO4 molecules, you can have the formula H4 S2 and O8, H4 S2 and O8, and due to heating one H2O molecule is lost, so what is remaining here, H2S2O7. So if you have to write the molecular formula of H2S2O7 or the structure of H2S2O7, take two sulfuric acid molecules and remove one H2O molecule here, that is here S double bond O, S double bond O, OH one is there, and one H is removed from this, S double bond O, S double bond O, OH as it is, and one O here, that is we have removed one H2O molecule, that is two hydrogen atoms are removed here. Remember here two OH groups are there, means one H is lost, again one H from this second molecule, and one O is lost here. Like this you can obtain the structure. When you draw the structure, you have to remember this basic thing, that is di means 2, pyro, that is when you heat sulfuric acid, two sulfuric acids are combined together and one H2O molecule is removed, and so if you remember this sulfuric acid, you can write the structure of di or pyrosulfuric acid. Now the next is peroxy monosulfuric acid. Remember, this peroxy monosulfuric acid is obtained by adding one oxygen in sulfuric acid. One oxygen is added in sulfuric acid molecule, you can obtain H2SO5. So the formula of peroxy monosulfuric acid is H2SO5. When you add one oxygen atom in H2SO4, you can have this formula. And what is the structure? Remember here, again one common thing is S double bond O and OH is common thing, and one oxygen is added here only, and so here S double bond O, S double bond O, OH, and one oxygen here I have shown like this. In this one oxygen is added, and so peroxy monosulfuric acid has the molecular formula or has the structural formula like this. Now peroxy disulfuric acid, that is two sulfuric acid molecules are there, H2S2 O8, and this formula is like this. Remember, these two molecules are taken, and so this is called as peroxy disulfuric acid, that is H2S2O8. Now, when one oxygen is removed by the sulfur, then it is called as thiosulfuric acid. That is, remember here, in thiosulfuric acid, the different bond is S double bond S. Here, in any of this acid, these 5 acids I have shown, here there is no any double bond between sulfur and sulfur, but this bond is different in thiosulfuric acid. So remember, in thiosulfuric acid, one oxygen is removed and it is replaced by sulfur, and so S double bond S, S double bond O, OH and OH. What is the difference between sulfuric acid and thiosulfuric acid? Here, in sulfuric acid we have 2 S double bond O, and here this oxygen or one oxygen is removed or replaced by sulfur, and so S double bond S, double bond O, and 2 SOH bonds are there. So this is the structural formula of thiosulfuric acid. So you have to remember what is the relation between all of these, and then you can write simply the structures of oxoacids of sulfur. Now we shall consider the oxoacids of halogens. Halogens have different oxoacids. How these oxoacids or names of these oxoacids can be remembered? Here we shall see on the basis of oxidation state. If the oxidation state is +1, here the molecular formula will be HXO. What is H? H is hydrogen, X is halogen, and O is oxygen. So here the oxidation state of X, here if you consider the oxidation state of X, that is halogen, here +1 and -2, and so oxidation state of X will be +1, and when the oxidation state of this halogen is +1 or it is less, then it is called as hypohalous acid. It is called as hypohalous acid. Like this, if you take the example of chlorine, if this X is replaced by chlorine, that means you can have the formula HClO, or you can say it is HOCl, and so it is called as hypochlorous acid. So the molecular formula of hypochlorous acid is HClO, and here the structural formula will be OHCl. Here there is single bond between oxygen and hydrogen and single bond between oxygen and chlorine. Here the oxidation number of oxygen is -2, oxidation number of hydrogen is +1, and oxidation number of chlorine is +1. Like this, here we have considered about the oxoacid of chlorine only. You can consider bromine, iodine, etc. But remember, hypohalous, this halous is replaced, this halogen is chlorine, so it is hypochlorous acid having the formula HClO. Now if the oxidation state is increased to +3, that means one oxygen atom is added here. The formula is HXO2. Remember, here you can calculate the oxidation state of halogen is +3. It is called as halous. Remember, hypohalous, less oxidation state, greater than it is called as halous, and here one oxygen atom is added, and so you can write this formula as HClO2. HClO2, that is, this is called as chlorous acid. Halous, so here you have to remember this is chlorous acid HClO2, and see what is the difference between these two structures. The common thing is the single bond between oxygen and hydrogen is there, single bond between hydrogen, oxygen and chlorine is there, and one double bond between chlorine and oxygen is increased. And so when we go from hypohalous to halous, that is hypochlorous to chlorous acid. Here one double bond between chlorine and oxygen is increased. So remember the difference between these three. Now if the oxidation state is increased to +5, that is one oxygen is again added, the formula is HXO3. It is called as halic. It is called as halic, and so you can call it as chloric acid. And so here the formula will be HClO3. It is chloric acid. One oxygen is increased. So if you see the structure, HOOCl, and again one double bond between chlorine and oxygen is increased. Here one oxygen is added, again one double bond between chlorine and oxygen is added. The next is +7 oxidation state, HXO4. 4 oxygen atoms are there, so here -8 +1, and so the oxidation state of halogen is +7, and it is called as perchloric acid. And if you consider chlorine here, it is perchloric acid, HClO4. What will happen again here? Again one oxygen is increased, so double bond between chlorine and oxygen is increased, and so in perchloric acid we have 3 triple bonds between chlorine and oxygen, one single bond between chlorine and oxygen, and one OH bond is there. So see these differences here. It is very simple to remember. First we have to understand only, if you consider +1 oxidation state, hypohalous, or you have to remember for chlorine it is hypochlorous. When one oxygen again is added, it is called as chlorous acid, HClO2. Again one oxygen is added, halic, so this is chloric acid, and when one oxygen is added, it is called as perchloric acid, HClO4. Remember, for these oxoacids, as oxidation state goes on increasing, the strength of the acid goes on increasing. You know, strength of acid is the tendency to give H+ ions. If the tendency is more, then the acid is stronger, and this strength is measured in terms of the dissociation constant of acid. If the value of dissociation constant of acid is larger, then that acid is stronger, and this value goes on increasing from this hypochlorous acid to perchloric acid. Remember here the value of Ka for hypochlorous acid is 3.5 into 10⁻⁸, and that for perchloric acid is greater than 1, and so this value is higher than this, so this acid is stronger than this. So remember, as oxidation state goes on increasing, the tendency of this acid to give H+ ions increases, and therefore the strength of the acid goes on increasing. Like this, you have to remember the oxoacids of halogens, and the important is of the chlorine. So here the names of oxoacids of chlorine you have to remember, and if you remember the molecular formula, you can write the structural formula of all these oxoacids.